Okay. So, in order to kind of put an interesting issue on the table, I'm going to do this paper is all about taking a limit that we think is illustrative, and I'm going to do it in a very incredibly casual way today, just to motivate some issues about how to kind of discipline or limit or guide thinking about how much should we allow for misspecified dynamics, how much should we allow for misspecified estimation. So I have to do some hand waving. I guess I should have put this up at first. I don't know French, but I guess this is a good translation. Doubt is not a pleasant condition, but certainty is absurd. So anyway, we're going to go with doubts today. So this is, I'm going to do something. I'm going to take what, in a lot of economic dynamics, there's a limit that people take, which can be revealing sometimes, and it's to go from discrete time to continuous time. And the reason we typically do this is not necessarily because we think we have continuous time records of data, but we think that sometimes interesting simplifications occur as we take this limit, and complicated characterizations will sometimes simplify. Now, there's been kind of a criticism of this whole ambiguity literature about, well, if you take continuous time limits, it's kind of things, its potency gets removed. And so I want to readdress this question, and it's going to help us think more generally about these issues of measurement and calibration. Okay, so here's how we write down a continuous time model, but I want to write down the discrete time counterpart of this. So this is written think of xt as a set of a set of observations, or the kind of the xt or the increments of xt. It's going to have a so-called. This is how it's going to evolve locally, and this is going to be a so-called Brownian increment. So let's see what this is in discrete time. So this is just going to be. So let me just write down a discrete time counterpart to this. Xt plus tau minus xt equal to, I'll put this mu, say, of xt. Think of xt as data observed. Iota is going to be some parameter that the decision maker doesn't know. Okay, so there's going to be an estimation problem here because the decision maker is going to have to be an econometrician. It's not going to know what iota is. Now that says dt, so that means I'm going to scale this by tau. Think of tau as the amount of gap of time between between observations. And then there's this term here, the sigma of xt. And in discrete time, this is going to be wt plus tau minus wt. So now under this model, what happens is that xt plus tau minus xt is going to be distributed normal mu xt iota tau is a sample interval, and this is scaled to have variance given by the length of the time interval. So this is a so-called increment of a Brownian motion. And a Brownian motion has the fact that if I take differences, the variance is given by how much time has elapsed. So the variance here is going to be tau times, say, sigma of xt, sigma xt prime. Okay. So both the mean and the covariance matrix scale by the amount of time that's elapsed. Yeah.
Did you put a comma right before the tau, the second tau?
You think about right there?
Yeah.
Sure. Now, tau scales the variance. So what scales the standard deviation? The square root tau. Okay. So now I've got a mean that's scaled with tau, and the standard deviation that's scaled by the square root tau. Now drive tau small. Locally, the consequences of the mean are going to become more and more irrelevant in terms of uncertainty of this, and it's going to all be dominated by the variance. In fact, this is a standard, this kind of estimating continuous time stochastic processes. This is kind of a key observation in that whole literature, in the sense that if you really look locally, the hard estimation problem is trying to figure out this guy, and that this guy is the easy estimation problem. And that risk, however, if you're thinking about it in terms of the risk here, the risk is all dominated by this piece here. It's kind of, this part here, this mean distortion here is going to get increasingly irrelevant as I make tau small, because the standard deviation scales in the square root tau, and the mean scales in tau. Okay, so that's what we're going to get out of a kind of a continuous time limit, this notion that this kind of scaling notion. And that's going to show up in the next kind of observations I make. Okay. So, any questions about this? Because this is just how continuous time embeddings work, and they work so that once you kind of look over very tiny intervals, it's dominated by the by this variance component. You have to really integrate up over intervals to get interesting stuff going on here. That has a variety of implications, and some outside criticisms of this literature are kind of related to this observation. So what I want to do is imagine, suppose we've got this. Suppose x is observed, and we'll just make it. We'll adopt this fiction that x is that we have the continuous record. Of course, we don't have continuous records, but we'll just adopt that fiction for simplicity here. So, if we want to learn about iota, I need to form a likelihood. That's how we typically do learning. We construct likelihoods as functions of this unknown parameter here, iota.
So you know the functions mu and sigma?
Yeah, right. So I'm gonna presume I know mu, I know sigma, and I don't know iota. You might ask, why don't I stick an iota there? Why not? Well, here again, this continuous time limit does some funny things in the sense of I can figure out this variance locally by just looking at observations very finely, and that would reveal the parameter value. So to make the estimation problem challenging, the challenging part is estimating this piece here. I mean, it's kind of a corollary to this observation over here. Okay, so I'm going to think about this as a challenging estimation problem, potentially, something that I have to use statistical methods for. This is just, locally this is like a normal likelihood function. So, the logs of normals are kind of quadratics. So this thing here has a quadratic term in the variance and the mean with the inverse covariance matrix here. I've got this term here. You might say, well, what happens to a term in like dx and cross product in dx? Well, that's going to be I'm just going to scale that out of all the different iota models. It's not going to contribute anything to the unknown parameter, so it doesn't contribute to the likelihood, nor is it particularly well defined in this limit. So anyway, I guess you can trust me that we know that normal likelihoods are these quadratics, and this is kind of the right thing. And then if I want to form what are the probabilities that I assign to the models, I just announce a prior. That's just how I initialize this L0. And then I just look at this LT across iotas and divide it by the sum of these guys. And that gives me the so-called posterior for model iota. So this is kind of the standard Bayesian calculation. I use the likelihood. The prior just shows up here, and then I produce this as a corresponding posterior distribution. So this is just when we do standard stuff for applied to this environment.